we talk about thermochemistry. So thermochemistry is a branch of thermodynamic study with a study of heat exchange and work by the system and surroundings. So it's very important that as we talk about thermochemistry, we understand some of the key terms that are very, very important. So we need to understand what heat is. So what is heat energy? How would you define it? So heat is a form of energy which is transferred from, of course, a body of higher temperature to where there is what? A lower temperature. That is heat energy. We also need to understand what specific heat capacity is. So we can say specific heat capacity is just the amount of energy that is required to raise a temperature of a given mass by just 1 degree Celsius. So the specific heat capacity may have different units depending on what you're talking about, different masses. For example, a specific heat capacity of water in terms of a gram is actually given to be 4.184 joules per degree Celsius, of course multiplied by grams, or preferably you can start with grams. Then in kilograms it's 4,184 joules per kilogram degree Celsius. So that's it about specific heat capacity. Okay, so now let's try to talk about let's try to solve the questions to help us understand more about this topic. Okay, so we have a first question there. Surroundings and the system. So when you're dealing with thermochemistry, basically in chemistry we're going to focus more on solutions and reactions. So let's say you have a beaker there and you've put reactants in this beaker. Of course, let's say they are in form of a solution. So the reactants that are inside there, we are going to refer to them as what? As the system. So then what is the surrounding? So the surrounding is going to be everything else around, including the container. So most of the people miss it. So a container is part of the surroundings. Okay. So from there you can put those things in your own ways to define what a system is and what a surrounding is. So a system is what you actually tend to focus on. Then we have got types of systems. What are these types? So we try to classify them in terms of exchange of heat or energy and matter. So we have what we call an open system. So an open system involves exchange of energy and what? And matter. So this can be a very good example of this can be talking about boiling water that is not covered. When you've not covered, let's say you've put some water to boil, then you've not put a cover there, maybe on a stove. Okay. So we are going to see that there's going to be exchange of matter. How? So the vapor that is going to be leaving the pot, that is what we are saying matter. Okay. Then you're going to find also that heat is going to be lost to the surroundings. The pot is going to be hot because we are saying the container is part of the surroundings. So that kind of a system is what we are calling an open system. We've got two more different types of systems other than the open system. So we have what we call a closed system. So with a closed system, there is exchange of what? There is exchange of energy. But there is no exchange of what? But no matter exchange between the system and the surroundings. So a very good example of a closed system is you've put water to boil, let's say in a pressure cooker, where vapor cannot be lost to the surroundings. So such a case, a pressure cooker doesn't allow vapor to move out of the pot. So we can say that it's a closed system. But of course, despite you covering the pot, if you leave it for some time, it is going to cool. meaning that there is exchange of heat energy. So as we are talking about energy in the context of the systems, what we're trying to say is we're referring to heat energy. So that's what we call a closed system. Then the last type of a system that we have to know about is what we call an isolated system. So what is an isolated system? As the name entails, an isolated system is going to be the type of system that doesn't exchange. So there is no exchange of both what? Matter and energy. So a very good example is a flask. So you find that when you put a liquid in a flask, the temperature is going to be maintained. Whether it's cold, whether it's hot, the temperature is going to be constant. Why? Because there is no exchange of matter and energy with the surroundings. Let's move on. What is internal energy? So we can define internal energy as the sum of all the energies of a system. So the summation of all the energy that a system is having or possessing is what we call the internal energy. Okay. So the energy that a system, the sum of all the energies that a system contains is what we call the internal energy. A very important concept and a very important thing to understand is what we call enthalpy. So what is enthalpy? So we can say that enthalpy, which is denoted by H, is given as a summation of the internal energy and pressure multiplied by volume, which in this context would not work most of the times. So that is how you determine the work of a gaseous of a gas, in short. Okay. So now we need to understand that enthalpy is a state function. So enthalpy is a state function, meaning that it doesn't depend on the steps. So whatever steps you may take, enthalpy is still going to be the same. So a very good example is going to the mountain. So let's say your initial position was down the mountain. So the distance that you're going to cover from that point to where let's say the displacement from the point where you started up to the top of the mountain is a state function. Of course, we know that you can't move straight all the way up. You're going to find ways, suitable parts of the mountains to move and climb up the mountain. So, but the displacement is going to be independent of your path. So that is a very practical example of a state function. Calculate the change in internal energy for each of the following. So it's very, very important for us to understand that the change in internal energy is actually given as a summation of heat energy of a system that can either be lost or gained and work. So we need to understand that in some of the cases, Q is positive, sometimes also negative, and we know this is denoting heat. So when heat is lost to the surroundings, it's negative, and that is in an exothermic reaction. And it tends to be positive when it is being gained. So such a reaction is said to be endothermic. Okay. So let's try to do with the calculations now given in the question. Okay. So calculate the change in internal energy. So for A, start with A. So the change in internal energy is going to be a summation of our Q and our work. So what is our Q is negative 47 plus 88 as our work. So the summation there is going to give you 41 kilojoules. So that is our internal energy of that system. Okay, again the change in internal energy for B is going to be the summation of what you have, 82 kilojoules plus negative 47 kilojoules. So what we're going to have is 35 kilojoules. Then finally, the last one, C. So the change in internal energy is going to be a summation of 47 kilojoules plus 0 work, which is still going to be 47 kilojoules. The question continues to say, in which of these cases do the surroundings do work on the system? So just like we've said that heat energy can be negative and positive, even work can either be negative or positive, depending on what's happening. So let's try to understand, when is work positive and when is it negative? So in terms of a gas, we can say that work is positive when the system, when there's work being done on the system. So work on the system is positive. So a very good example is when you have a gas in a container, then you compress the gas, meaning that what is going to happen is the container is going to become smaller. So meaning that you are affecting the system. You are doing work, or you are performing work on that system. Okay, now when is it negative? So work gets to be negative when the work is being done by what? By the system. So work by the system is negative. Why is it negative? It's negative because the system is losing energy when performing work on the surroundings. Okay, so from there we are able to answer the question now that we've been given. So in which of these cases do the surroundings do work on the system? So we are saying when work is being done on the system, so we are saying that when work is done on the system, it is positive. So all the cases where it is positive, we are going to say the work was done on the system. And in this case, it's A. Alright. So before we move on, I'll have to make some of the important things for you to note. When you are taught to determine the work is given by pressure change in volume in terms of gases. Okay. So in this case, it means that there is expansion. Okay. In a case where there is compression, it is negative P change in V, because we expect that the temperature, or rather the volume, is going to be reducing. Let's say from 10 to 4. So the change in volume in such a case will be 4 minus 10, which is going to be negative 6. But we don't want our work to be negative, so we put a negative to be part of the formula whenever the volume is what? Reducing. Alright, the next question says, when 155 grams of water at 20 degrees Celsius is mixed with 75 grams of water at 80 degrees Celsius, assuming no heat is lost to the surroundings, what is the final temperature of the water? So given that the specific heat capacity is 4.18. Okay, so it's very, very important that for you guys to note that whenever you are asked to determine the heat that is either being lost or gained by a system, we work with this formula. So the heat that is either lost or gained is given by mass multiplied by the specific heat capacity and the change in temperature, where the change in temperature is going to be given by the final temperature minus the initial temperature. Okay. So whenever you're given two things to deal with, what you're supposed to do is you're supposed to equate them. So in this case, what have we been told? So we've been told we are mixing two waters. We're mixing two containers of water, of course, of different temperatures. So we can say alright, we move on to the third question. So when 155 grams of water at 20 degrees Celsius is mixed with 75 grams of water at 80 degrees Celsius, assuming no heat is lost to the surrounding, what is the final temperature of the water? So you are mixing water at different temperatures, okay, and of different masses. So whenever you are asked to determine the heat that is either lost or gained by a system, we work with this formula, where M is the mass, C is the specific heat capacity, and the delta T is the change in temperature, given by the final subtract the initial. Okay, so whenever you're dealing with two systems, one gaining and one losing, we are supposed to equate them. So say Q1 in this case is going to be equivalent to Q2. And we need to put a negative sign to show that on one side it is going to be lost. So where there's a high temperature, we expect that the temperature is supposed to reduce, meaning that there's a loss of heat. So we can put a negative for the side that we are going to put a high temperature. So in such a case, which one is the high temperature between 20 and 80? So it's 80. So 80, that's where we're going to put where there's a negative. So what's the mass? The mass is 75 grams. What is the specific heat capacity of water? It's 4.18. Multiplied by the change in temperature, so we don't know the final temperature. The initial temperature was 80. So not forgetting that there's a negative there. On the other side, we have got 155 grams of water. The specific heat capacity is still 4.18. The change in temperature, the final we don't know, the initial is 20 degrees. Okay, so we can try to compute that now. So on the left hand side and the right hand side, we can see that we've got something that is common. So it's very advisable that when you're dealing with a same substance of the same specific heat capacity, you divide so that you save on time. So what are we going to remain with? We're going to multiply now negative 75 by that. So we have negative 75 T final. Negative 75 multiplied by 8 is going to give us what? So negative 75 multiplied by negative 8. So we have positive 6,000. So plus 6,000. On the right hand side, we have got 155 by T final. Then you have 155 multiplied by the negative 20. So we have negative 3,100. So from there now, we need to determine we need to correct the like terms. So what are the like terms in this case? So we have this part having the T final and that part having the T final. They are like terms. So we can make them be the one side. So 155 T final plus 75 T final is supposed to be equal to, so the other side we have a 6,000 plus 3,100. So 155 plus 75 is giving us 230. Then on the other side, 6,000 plus 3,100. 6 plus 3 is 9. So it's 9,100. So divide 9,100 by 230. So what I'm getting as my T final is actually 39.6 degrees Celsius. So that's the way you deal with questions whenever you are asked two things are being mixed at different temperatures. So you just come up with the Q values, add a negative on a side where there's a high temperature because you expect that there will be loss of heat. Alright, question 4. A piece of iron weighing 20 grams at a temperature of 95 degrees Celsius was placed in 100 grams of water at 25 degrees Celsius. Assuming that no heat is lost to the surroundings, what is the resulting temperature of the iron and water? So in this question, like a previous question, here we are given two different materials. We've been given iron and water, which have got different specific heat capacities. So the same formula is going to work. So what we're trying to determine is the final temperature, because they are saying the resulting temperature. So what piece of information have we been given? We've been given the mass. So we'll start with iron. So for iron, we've been told the mass is 20 grams. We've also been told the temperature is 95. Then we've also been told, so we've been given the mass. Okay, we've also been given the specific heat capacity, which is 0.451. Okay. So on the other hand, for water, what have we been given? The mass was 100 grams. The temperature was initially 25. Then the specific heat capacity, which we already know, is 4.18 for water. Okay. So like we said, we're supposed to come up with an equation where we say Q1 should be equal to Q2, meaning that the heat that is lost is supposed to be equivalent to the heat that is gained by another substance. So we need to put a negative sign where there is loss of heat. So whenever you have got two different temperatures, we expect that the one that is higher is expected to lose according to the law of thermodynamics. So we'll put a negative on the side for iron. So we can now plug in. We know that the heat gained or lost is given by the mass multiplied by the specific heat capacity multiplied by the change in temperature. So what we have is our mass is 20. So it's a negative outside. The specific heat capacity is 0.451 multiplied by the final temperature. We don't know. The initial, it's 95. So what we have on the left should be equal to what we have on the right. So what do we have on the right hand side? So we have got the mass of 100. The specific capacity is 4.18. Okay, due to lack of enough space, I'll write it down. Multiplied by the change in temperature, which is the final, minus the initial, which is 25. So from there now we can do our computations and simplify what we have. So let me just create some space here. Okay, so what do we have? So on the left hand side, if you get your calculator, you're multiplying negative 20 multiplied by 0.451 multiplied by, so even just before we multiply this, just overwrite what that is giving us. So we have got negative 9 negative 9.02. In the brackets, we've got T final minus 95 being equal to the other side. We've got 100 by 4.18. So it's going to be 418. In the brackets, we've got T final minus 25. So negative 9 by the T final is going to be negative 902 T final. Then the negative 9 multiplied by the 95, it will become positive. So 9.02 multiplied by 95, we have positive 856.9. Then on the right hand side is 418 multiplied by T final. 25 times 418 is giving us minus 10,000. $450. Okay, so we correct the like terms. So this can go the other side, and this side we are going to have 10,450 plus 856.9. On the other side, you've got 418 T final plus 9.02 T final. Okay, so if you add 10,450 plus 856.9, I'm getting 11,306.9 equal to 418 plus 9.02, 427. So 11,306.9 divided by 427. What we have as our T final is 26.47 degrees Celsius. So what is very important is to note that the higher mass with a higher specific heat capacity has got a bigger influence on the temperature as compared to a low mass with a low specific heat capacity. So in this case we had water with a great mass and also a greater specific heat capacity as compared to a high one. So it had a greater effect on the temperature. So it is very easy for iron to cool down than to raise the temperature of water. Now we've been told a copper forceps which has got a mass of 500 grams was accidentally left on a heating mantle until it had a temperature of 35 degrees Celsius. A student then placed the forceps in 70 grams of water at 20 degrees Celsius to cool it off. Calculate a specific heat capacity of a copper forceps with a final temperature of the water of 27. So they want us to determine the specific heat capacity of a copper forceps. So even without wasting your time, it is not different from what we've been looking at. So you can pause the video and try it out. So we are saying we should put the negative on the side where we expect the temperature to be decreasing. So you go for the one that is having a higher temperature. So in this case, a copper forceps before being placed in water, it had a temperature of 85 degrees Celsius. Okay, then it was placed in the water that was at 22 degrees Celsius. Okay, so which one is bigger? It's a 35. So where we are going to put the negative, that's where we're going to have a copper forceps. So the mass was 500. Remember, our Q is determined by MCAT, the mass specific heat capacity multiplied by the change in temperature, where the change in temperature is equal to final temperature minus the initial temperature. Okay, so we have the mass there multiplied by, we don't know the specific heat capacity of the copper forceps. The change in temperature, do we know the temperature? The final temperature we know is 27. So it's 27 minus the initial, which was 35. So on the other side, for water, what do we have? So the mass was for water is given in the question to be 70. The specific capacity is 4.18. The change in temperature, the final was 27, of course. The initial was 22. So remember there's a negative here because it had a greater temperature, so it was losing. So get your calculator, subtract 27 minus 55 in brackets there is giving us negative 8 multiplied by the 500. So 4,000. So we have a negative outside, then 500 by the difference there, which is 8, is giving us negative 4,000 multiplied by the C, which is supposed to be equal to the other side. 27 minus 22 gives us a change in temperature to be 5 multiplied by 4.18 multiplied by 70. We have 1,463. So we can clearly see that on the left hand side we have got a positive value now after multiplying the negatives. So we need to divide that value, the 4,000, into the 1,463 for us to get a specific heat capacity. So after dividing, the answer that I'm getting is 0.365 0.75. So joules per degree Celsius multiplied by grams. So that's our specific heat capacity for the copper for step that was being used in this question. Alright, question 6. A 0.196 gram sample of quinone with that formula is burned in a bomb calorimeter that has got a specific heat of 1.56 kilojoules per degree Celsius. The temperature of the calorimeter increases by 3.2 degrees Celsius. Calculate the energy of combustion per gram and per mole. So first of all, what we're going to do is we need to determine first of all the Q, which is the energy that was either lost or gained by the calorimeter. So after from there now, we can now determine the per mole and per gram. So where they are saying per gram, we'll use the mass, which has been given. Okay, so what are we going to do? So we start. So in the question, what data have we been given? We've been given the mass, 0.1964 grams. The formula is C6H4O2. So the specific heat capacity, of course, has been given to be 1.56 kilojoules per watt. The temperature increases by that. So when they say the temperature increases, so that is the change in temperature already. So we determine our Q. Okay, so we're trying to determine Q now, the energy of combustion. So our heat is determined by MCAT, remember. Okay, so what is our Q in this case? That's what we're trying to determine. The mass was the mass that was being bent in the calorimeter was 0.964 grams. The specific heat capacity was given to be 1.56 kilojoules per degree Celsius, multiplied by the change in temperature was 3.2 degrees Celsius. So this will divide. Okay, so the specific heat capacity, of course, is supposed to be per gram as well. Okay, supposed to be per gram. So it's degrees Celsius per gram. Okay. So what do we do now? So we need to get our calculator and punch that. So 0.1964 multiplied by 1.56 multiplied by 3.2. What we have is our Q in terms of joules, kilojoules it is. So our Q is 0.9804 kilojoules. So that is in terms of kilojoules. Now they want us in the question, they want us to find per gram and per mole. So we would want this value to be a bit bigger. So a kilojoules means we multiply by 1000 for it to be in joules, which is going to be 980.4288 joules. So we need to determine per gram and per mole. So where they're saying per gram, you divide by the mass in grams. So what was the mass in grams? 0.1964. So our Q is going to be 980.4288 joules divided by 0.1964 grams. So what I'm getting is 4,902 joules per gram. So it's per gram because we've divided by the mass. So in the question it's also saying per mole. So how do you determine per mole? So we determine per mole by dividing by the number of moles. So how do we get to determine the number of moles? So we determine the number of moles by dividing the mass by the molar mass. So the mass has already been given. So you look at quinone, which has been given in this case. What is our quinone there? So our mass is actually 0.1964 gram. That's what the question had told us. So we need to determine the molar mass of this compound. So it's C4C6. So we need to multiply that by. So how many carbons do we have in that case? There are 6, and each carbon has got 12.01 molar mass. For hydrogen, it's 1.008 plus. So I'll write down there because I don't have enough space. For oxygen, it's 15.994. Okay, so you get your calculator and divide there. So 0.1964 divided by that. What I'm getting as my number of moles are 0.0018. So these are the number of moles. Okay. So after getting your number of moles, you need to plug in where we are at the mass now. You plug in. So let me just create some space. Okay, so the number of moles that we have are 0.0018 7979. So moles. So our answer is going to be 539 295.7 joules per mole as required per question. Okay. So that's it for this video. I just hope that the basics that I've given you will help you to build your background in thermochemistry. So watch out for the next video that is going to help us understand more questions in determining the change in enthalpy using the enthalpy of fusion as well as the bond energies and S's law as well.